Welcome back to Finite Element Methods, Math 574 here at the University of Tennessee. This is our fourth class. We were talking last time about multi-index notation, and I was trying to convince you that it was quite useful for doing certain things, one of which is writing out polynomials that are kind of multi-dimensional polynomials where the range is RD. Of course, I can think about polynomial systems of equations from RD into RD by thinking about this as being just one component of a polynomial system, but that's not so important at the moment. I want you to consider this example where thinking about polynomials that map RD into R. So normally this would be difficult to express all the components, all of the terms for this polynomial, but using multi-index notation, it comes out very simply. For example, if we have a polynomial of degree n or less, then we can express it like this, where these are the coefficients. And this notation I defined above, x raised to a multi-index power, simply means that we take each component of the vector x and raise it to the associated power and then multiply all those terms together. And so that gives us terms of various orders. The order is determined by the order of this multi-index. And by order of multi-index, remember, that was defined as, and I'll erase this in a second, that is defined as I take the sum, I think I used k equals 1 to d, and I just add up all of the orders of each one of the multi-indices, each one of the components of the multi-index, and that gives me the total order. So let me show you an example of this to show you how it works. And we're ultimately going to use this not for polynomials, but for derivatives. Although, because we're talking about finite elements and we can be talking about finite elements in arbitrary space dimensions, it could be a quite useful notation for us, actually. Suppose, for example, I want to express a polynomial which takes R2 into R. So, and let's suppose that the degree of this polynomial is less than or equal to 3. The degree might not be exactly 3, as I'll explain in a moment. If you know a bit about polynomials, you know why right away. But so let's express a generic polynomial of degree up to and including 3 that takes R2 into R. What should that look like? Well, as I said above, the total degree appears here in the polynomial, or the maximum total degree, maximum possible total degree. It might not be exactly that, but so we're going to sum over all terms whose order in the multi-index is less than or equal to 3. These terms have coefficients, of course, and these monomial terms here. So let's think about, what does the first term look like? Well, what is allowed with multi-indices is remember, multi-indices are kind of vectors. Well, they are vectors. And the components of these vectors come from this set n0, where n0 is the counting numbers plus 0. And they're d-tuples. And so they're vectors, each of which component comes from n0d. So it is possible that, well, that I have a multi-index of order 0, because I could pick all zeros out of this set. In fact, that is the first coefficient that we have. That's the 0 order coefficient. Now, there's going to be 2 indices in this case in my multi-index, because we said d is equal to 2. That's this number here. All right, and the total degree goes here. So I'm going to use, for these multi-indices, what's the natural one of 0 order? It's the one whose coefficients, or sorry, components are 0, 0. What about the order 1 terms? Well, we've got either 1, 0 or 0, 1. Okay, and the 1, 0 term is going to be x raised to the alpha, where alpha is 1, 0. So that means x1 has 1 power and x2 has 0 power, or in other words, x2 to the 0 power just becomes 1. So we can drop that guy, right? So everybody sees that this term here, or this extra product would be, extra term in the product would be x2 to the 0 power, but that's just 1. And what about this term? A01. Well, that means x1 is going to have the power 0, x2 is going to have the power 1. So that is all the possible first order terms. So there's a first order coefficient of this type and a first order coefficient of this type. Notice that if I'm thinking about standard polynomials from R to R, then there's only one first order coefficient, there's only one second order coefficient, and so on. But when I'm thinking about polynomials from RD into R, then there can be more of each type. For example, for the second degree terms, there are exactly 3 coefficients. One possibility is alpha equal to 2, 0, then alpha equal to 1, 1, and alpha equal to 0, 2. Those are the 3 possibilities. So each one of those represents a coefficient associated to a different term. For example, 2, 0 is going to be x1 to the 2 power, x2 to the 0 power, which I'm going to leave off because it's 1. A1, 1, what is that associated to? Well, that's the multi-index 1, 1. So that's going to be x1 to the 1 power, x2 to the 1 power, or the first power. What about the third one? The third one is alpha equals 0, 2. So that's x1 to the 0 power, x2 to the 2 power, the second power. Finally, we can get to the third order coefficients. So what are the possibilities for third order coefficients? Clearly, it's going to be 3, 0, 2, 1, 1, 2, and 0, 3. And of course, we produce these 4 terms in that polynomial expansion. So I hope you'll agree with me that this is a whole lot more compact way of writing the polynomial of the general polynomial of degree at most n equals 3. If I had to write it out in more details, then I'd have to use this much clunkier notation. I like this one a lot better, and I hope you see that this multi-index notation makes that possible. Now, why am I saying a polynomial of degree up to n equals 3? Well, each one of these could have coefficient 0, right? And so that would be a polynomial of possibly second order rather than third. So that's why I made that distinction. Okay, so that's the multi-index notation. As I said, we're mostly going to use that in connection with partial derivatives. And I want to talk to you about something called weak derivatives. So it turns out that, of course, for finite elements, we're talking about doing approximations of solutions to partial differential equations. And partial differential equations involve partial derivatives. Partial derivatives come in many different flavors, right? So I'm first going to tell you my general philosophy about taking partial derivatives whenever the domain of the space is a subset of RD. We're going to call that subset usually omega. For example, what if I have a function that is a function that has R continuous derivatives and is a function from omega, a subset of RD, into R. Sometimes, to be really specific about such spaces, I'll write something like this. Let me make a little room here. So if I really want to be specific about the range and the domain, I'll do something like that. That means, so this notation here means that my domain is the set omega and my range is R. So these are real valued functions. Okay, so they're usual sort of functions that you're used to. So now if I have a function whose range is a subset of RD, then I have not just, you recall this from your calculus days, I have not just one type of derivatives, but kind of a multiplicity of derivatives. These are called partial derivatives, and they come in different types. So what does this notation mean? This notation means that I can take a derivative of up to order r, and it's still going to be a continuous function. It's still going to be a continuous function from omega into r. What does that mean? Well, what I mean is you can make all the partial derivatives that you want of any order up to and including r that you want, and those are all going to be continuous functions. But what do those partial derivatives look like? Well, precisely using my multi-index notation, I can write this in a very concise way. So the partial derivative of, well, we sometimes call this the alpha partial derivative of v, can be written as partial order alpha. So this is the total order that I'm going to be using of v. And then I can tell you the specific type of partial derivative I'm looking at using the multi-index notation. Here's an example that really should bring this home. Suppose that I'm in 3 dimensions and I want to express a fourth order partial derivative of a certain type. Now you should know that there are many different fourth order derivatives. We could write them down out, and you can use combinatorics to figure out how many you have. For example, you have 4, 0, 0, then you have 3, 1, 0, 3, 0, 1, blah, blah, blah. So there are lots of different types. The total order has to be equal to 4. The one that I'm going to choose is this specific fourth order partial derivative, the alpha partial derivative, where alpha 1 is 2, alpha 2 is 1, and alpha 3 is equal to 1. So the total order is 4, as you can see by adding up these 3 numbers. 2 plus 1 plus 1 is 4, right? So, but what does this particular partial derivative look like and mean? Well, it means we're going to take the partial of the function. We're going to take 2 derivatives with respect to x1, 1 derivative with respect to x2, and 1 derivative with respect to x3. So this is a fourth order partial derivative. The multi-index notation makes this very compact because instead of writing all this stuff over here, I simply can write this and tell you what that vector is. So I hope that you see that this combined with that is a whole lot simpler than writing out all that. Remember, a good notation is supposed to save you time and energy. It should be easy to look at, and sensible. Okay, good notation is both allows for compact writing, but it also has to be sensible. It has to feel right, I guess. Now, these multi-indices allow for us to define these spaces that I just alluded to very concisely and quickly. What does this space mean? I kind of used this before I said what it means because I thought, well, you probably are used to seeing, you're probably used to knowing what a C2 function is for functions mapping omega into R, where omega is from a set or the space RD. You probably haven't seen or much less familiar with the multi-index notation and how quickly and compactly it can be to write such information. For example, if I want to express this space Cm quickly and easily, I can say that's a set of all functions v that are continuous, such that all the partial derivatives, all the alpha partial derivatives of v are also continuous for all orders from 1 up to m. Okay, and m is here. Now, why did I start at 1 instead of 0? Well, I've already expressed the fact that the 0th order partial derivative is continuous, and the 0th order partial derivative is simply the function itself. Likewise, if I'm talking about the function space where I'm thinking about functions over omega bar, what is omega bar? Omega bar, that is the closure of omega, and we'll talk a bit more about closure before, but for point sets, closure is pretty easy, right? So usually I'm starting with an open set, and if I want to close it, what I do is I add the limit points of that set. So I'm assuming you're familiar with that. So this is the set of all functions v in C closure. continuous functions from omega bar, that's the closure of omega, into R. I've dropped the R here because that's usually understood. I drop that when it's understood that they're real valued functions as it is here, such that the alpha partial derivative of V is also a continuous function over omega bar for all multi-indices of order between 1 and m. Now, what about C? So that makes writing these two function spaces very quick and easy. Okay. Now, what does it mean, by the way, for a function? What does it mean for a function over omega from Rd into R? What does that mean for that function to be continuous? What does it mean if I say that function is a continuous function from that set omega into R? Well, one of the definitions that's most convenient in this case is what we call the sequential definition of continuity. It means that if I have any sequence converging to X, then the sequence f of xn, for example, converges to f of x. All right. So that's written. I'm just going to give you that quick notation. For every sequence that converges to x in the domain, that a function is called continuous if and only if this sequence converges to f of x. That's the easiest definition when we're dealing with functions like this, where the domain is a set, open or closed, whatever, of RD. I find this sequential definition is easiest, but you could use other definitions involving epsilons and deltas as well, which turn out to be equivalent. I like this one the best. But I'll assume that you have some familiarity with that, and we won't belabor that point. Now, this is kind of independent of the multi-index notation, but by this set C infinity, we mean the intersection of all the sets Cm from m equals 0 up to infinity. So this contains functions which are continuous and have continuous derivatives up to any order that you like. And the same with C infinity over omega bar. These are continuous functions whose derivatives of any order that you want to examine are also continuous functions. What do we mean by this set called the support of f? You've probably heard of this definition as well. So suppose that omega is an open subset of Rd, f, and suppose that f is a continuous function. We need f to be at least continuous. Well, for this to make for this to make the most sense, I guess. We could have a larger set of functions that we describe whose support we can define, but this makes a lot of sense because at least we have what are called point values for the function. Then the support of f is the closure of the set of all points in omega such that f of x is not equal to 0. Okay, so this set is called the support of f. And the easiest way to motivate this is to show you an example, which I'll do in a moment. We say that f has compact support if and only if the support of f is a bounded set. We know that the support is already a closed set because we obtain it by closure. So we say that f has compact support if, in addition to being closed, is also a bounded set. And we have to have one other thing for this kind of to be meaningful. We need the support of f to be a proper subset of the open set omega. Okay, so this is what we mean by proper subset. I mean, if I write this, then I mean that's a subset, but it could also be equal to the parent. But if I write this, this is saying that it's truly a proper subset. Proper subset is not allowed to equal the parent set. So I think that's pretty standard notation, and so I won't belabor the point there. All right, here's a good example of the support of a function. Suppose that omega is some open interval, which is non-trivial. I say non-trivial because I want A to be strictly less than B for this to make sense. Suppose that f has the following graph. It's going to be 0, and then it does something which is non-zero, and then it's 0 again. Okay? So this is usually how we're going to use the support of the function. So then the question is, well, what's the set of points for which f is non-zero? The set of points for which f is non-zero is x in, so remember our definition, it's going to be x in the domain of definition omega. So what was the domain of definition? That's going to be between a and b, strictly, such that f of x is not equal to 0. So that set, we'll start with that set, okay? That's not exactly the definition of the closure. Let's start with this set. That set is equal to CD, not including C and D, right? Because at C and D, I just said the function is equal to 0. It's equal to 0 here, and then for all points behind it, and it's equal to 0 here and all points after it. Now, what we do is we take this set and we're going to close it. We're going to add the limit points for this set. Well, what are the limit points for this open interval? The only limit points that don't already exist in the set are the endpoints C and D specifically. So that's why I say down here, the support of f is equal to the closed interval from C to D. All right, so this function here looks like has compact support because the support is closed. It's also bounded because we assumed, well, let me go a step further. We'll assume that this is greater than minus infinity and this is less than infinity. You probably don't have to say that because we weren't working with extended real numbers, but there are these things called the extended real numbers, which are useful sometimes. So we know that this set is bounded. It's already known that it's compact, or that it's already closed. We know that it's contained inside of AB, so we say that F has compact support in this case. Now, it turns out that this always amazed me, and it amazed me the first time I saw it. It amazed me that the next definition made sense. That there could be a set of functions that were C infinity and that had compact support. This function here that I've drawn up here, it doesn't look like it's a C infinity function. It looks like maybe it has one continuous derivative here and here, but it doesn't look like a C2 function. That's because when I take the derivative of the function here, it's always going to be 0. But when I take maybe the second derivative here, it looks like maybe the second derivative is not going to be 0. So it doesn't look like this is a C infinity function, okay? F looks like maybe at best C2, maybe C3, I don't know. It always amazed me that this set had any members in it at all. But once you see an example, you can't unsee it, and then you know forever that there are things in there which are non-trivial. So here's the professional definition of this. Suppose that omega is an open set. Often it's a bounded set as well. That's usually how we're going to use this. Suppose that it's an open and bounded set. Then, slight mistake here. I forgot to include the omega. Okay, so I'm defining C0 infinity omega. That's the set of all functions that are C infinity and they have compact support. Okay, so maybe it's not surprising to you that such functions exist. It was to me. But let me show you an example that once you see it, you'll understand why it's true. Suppose that omega is equal to minus 2 to 2. Could be anything I want, but all I really need is for it to contain the interval -1 to 1. Okay, so -2 is about here, 2 is here. Okay, so that's the interval in question. And now the function I'm going to define has stuff going on for x in absolute value less than or equal to 1. So I'm going to define this function as having something going on between -1 and 1. But for the absolute value of x greater than 0, I'm simply going to define that function to be 0. So it's always just going to be 0. Now I claim that based on the definition of this function is C0 infinity. So my claim is that f is a C0, did that wrong, C0 -2 to 2, okay, C0 infinity function. So is it true? I'm going to ask that you prove this in either the next homework or in the current homework or the next one. And it's not hard to verify. It turns out that all of the derivatives of f as I approach -1 from above approach 0. In fact, all of the derivatives, so this function is defined at x equals -1 and +1, and you can find the derivatives of that function. You kind of have to do that in, well, let's see. So does this make sense? Right. So I think I have to be a little more careful here, don't I? So let's define it like this. There. That makes a bit more sense. The reason why it didn't kind of work beforehand is because, well, if x is equal to plus or minus 1, then this is equal to 0. I'm dividing by 0, so that shouldn't be allowed. But this is fine, right? So I claim that, of course, the derivative on this side, all derivatives of all orders is equal to 0 on that side. To figure out what the derivative is from this side as I approach 1 or I approach -1 from above, well, I have to do a limit there. And it's pretty easy to show that all of the derivatives of all orders at -1 and +1 are exactly equal to 0. So this function turns out actually to be a C0 infinity function, as long as the interval on which this thing is non-trivial is completely contained within the interval of total definition, -2 to 2, which it is. Okay, -1, the open interval -1 to 1 is a proper subset of the open interval -2 to 2. Okay, so everything is kosher there. Okay, so why do I care that such functions exist? Well, it turns out that if I have a set like this, then it becomes a very useful set for doing analysis. Now, there's also a set of what are called analytic functions. Okay, analytic functions are functions which can be described by their power series expansion at any point of the domain of definition. And this is not one of those functions. Okay, these are not the same function classes. So in other words, this is not equivalent to the set of analytic functions. Why? Well, because if I were to do a power series expansion about that point, what would I find? Well, I would find that the only function that has the power series, or well, if I use power series at this point, the only function I would derive is the 0 function. That's clearly not the same as this function. Okay, so the analytic functions can't be equal to this set of functions, even though analytic functions and C0 infinity functions are both of class C infinity. In any case, if you know anything about analytic functions, you'll know the distinction there. These are not the same. Right, so I need to know what are these Lebesgue measurable functions too. So I think probably, even if you've never had a course on Lebesgue measure theory, you've seen these functions floating around some way or somewhere or other. Now, if you've had the course 545, then you've seen these functions. Sometimes professors will introduce these function spaces in 547 and 548. When I taught that course a long time ago, many years ago, I introduced those function spaces in 448. And so most of you here at the University of Tennessee take 447 and 448, so you've seen these before. Now, there are some of you who haven't seen these function spaces before. Um, and if you haven't, shoot me an email and maybe we can set up a meeting to talk about them. Or if you're a little bit embarrassed to admit that, then you can go do a little Wikipedia search or grab your favorite book on analysis and look these things up, and you'll find a good description of them there. For the most part, I'll tell you exactly the things that we need to assume about them, and so you don't need to go kind of on your own there. Our treatment will be more or less self-contained. So what do I mean by the LP functions? So I mean functions which are Lebesgue measurable from omega into r, such that this integral is finite. Okay, the integral of the absolute value of f to the p power. P is any number between 1 and infinity, not including infinity. For p equals infinity, you have a slightly different space of functions than these integral, these spaces defined by integral finite integrals. In that case, you have what are called the well, it's the L infinity space, and it's functions whose essential supremum is bounded. If you know about a little bit about measure theory, but we're not going to belabor that point here. And we'll only define these for p between 1 and infinity. In that case, these function spaces are defined via these integrals, which we require to be finite. Okay, so the LP spaces, it turns out, the reason why we're so doggone interested in them is because they are Banach spaces. Remember we defined what Banach spaces meant last time. We said that Banach spaces are spaces for whom all of the Cauchy sequences are convergent. And so they're quite useful to us. They're what we call complete Banach, or complete normed linear spaces. The LP spaces are Banach spaces as long as we use this object for our norm. L2 is just the Banach or the LP space where P is equal to 2. Okay, so this turns out to be a Hilbert space, so it has a little more structure than the Banach space. It also has an inner product, and the inner product in the case where P is equal to 2 is this inner product that I'm showing here. So you should be able to quickly show on a napkin that this is the right inner product. And the way we know that is, well, if I wanted to find the norm on that space, then it should be given by taking the inner product of the function with itself and taking the square root. Well, you can see if I do that, then what I get is the square root of the integral over omega of the absolute value of f squared. Why absolute value of f? Well, why absolute value of f squared? Well, it's the same as f squared in this case, and I take f and I test it against itself, and so I'm going to get f squared in the integral, and that's precisely what I need to get in the in this interior here for this norm. So you can see that it jives with the norm that we've already prescribed for this Banach space, but it has more structure. It has the structure of a Hilbert space because it also has an inner product. Okay, great. So those are the LP spaces that we need. Now I need a little bit more because I want to define these weak derivatives, and I can define weak derivatives for functions which are even weaker than LP functions. In fact, I can define weak derivatives for things which are what we call locally LP. So a function, and again, we're not defining all this stuff for the simple sake of being abstract. We're defining it because we're going to use this stuff later. Mostly, I'm going to use the L2 spaces, and you won't ever have to worry too much about LP spaces. But we may talk a little bit about what are called nonlinear equations ultimately, and then we will need this machinery of talking about LP functions and ultimately what are called Sobolev spaces based on LP functions. But in any case, again, don't worry if it's going over your head at the moment. We're going to slow down and we're only going to use what we need, and we're going to keep this discussion self-contained. A function from omega into R, where omega is a subset of RD, is called locally P integrable, and we write V in LP loc. And that means that for every x in omega, there is an open set D such that x is in D and the closure of D is a proper subset of omega. So usually omega here is open. I should say that. So usually is open and bounded. Okay, so that's the situation we'll be using this mostly, or for which we'll be using this mostly. Okay, so what we have here is our domain of definition. And for every point x, we need to find an open set which contains x such that its closure has to be a proper subset of the original set omega. So here's our set omega, and this, of course, is our set D. And that doesn't look like a good D here. Let's see if I can improve upon that. There we go. Okay, so the closure of D has to be a proper subset of omega. That means that I'm talking about points which are not on the boundary. Okay, so if and only if we're talking about points which are not on the boundary, there has to be an open set D. We call this an open neighborhood, right? Such that its closure is wholly contained in omega, and V has to be an LP space over that open set D. So that means that locally, for each point x, this function is a nice LP function, but it could get really, really hairy and wiggly and weird near points. Okay, it could be, or the boundary specifically. Near the boundary, these functions could oscillate more and more wildly. So, for example, here's a function which would be L1 loc or whatever. Suppose that near the boundary, it starts to wiggle a lot. Okay, but suppose that, if I zoom in on any point, it's just like a nice, if I zoom in enough, it just looks like a sine wave. So a sine wave is a perfectly nice function, but what I'm requiring of this function is that it wiggles more and more as I get to this boundary point. So that function, if I take it as a whole globally, it might not be an LP function. However, if I look at it at any single point and zoom in, then it's a nice smooth enough function when I zoom in. So these functions are kind of nice locally, as long as you're willing to zoom in enough, but they might get arbitrarily bad near points, especially boundary points. And that's my little remark here. They can behave kind of arbitrarily badly near a point. Now, if I know that a function is LP, is it LP loc? The answer is yes. If it's LP, that means I can show fairly easily based on the definition that it's locally LP. However, um, if I have a function which is LP loc, is it going to be an LP function? Not necessarily. So this function space is a little bit bigger than LP. So if I think about these function spaces as being in terms of sets, then in here is LP. So I know that if a function is LP, then it's going to be LP loc. No problem. But this function space is bigger than this guy. So there are functions which are LP loc, which are not LP. Now, I will find this, this is sometimes called a variation or a calculus of variations lemma. I'll find this quite useful from time to time. And it says, if V is an L1 loc function, so that's this definition up above where I'm using P equals to 1. If I have functions which are a function which is L1 loc, and omega is a non-trivial open set of RD, if I find that when I integrate over omega V against this quote unquote test function phi, if I find that I always get 0 for all phi in C0 infinity, so these are the test functions that I'm particularly interested in. Remember, I just defined this class of functions and I said, look, this class of functions is generally non-trivial, or at least I showed it's non-trivial for intervals. Then, if this happens, then it must be that V is almost everywhere equal to 0 in omega. I hope everyone knows about this notation, almost everywhere. It means that it's true, the statement that I'm making is true, except for a set of points that have at most measure 0. Well, measurable set. If it has at most measure 0, then it's a set of measure 0. And now comes the big definition that I want to make, and that is the so-called definition of what we mean by the weak derivative. Let omega be a non-trivial open set in RD and assume that V and W are L1 loc functions. Because as I said, I can define weak derivatives for really badly behaved functions, actually. Potentially badly behaved. Let alpha be a multi-index, then W is called the weak partial, well, it's called actually the weak alpha partial derivative of V, if and only if it satisfies this integral equality. If I integrate V against the alpha partial derivative of phi, this thing always exists because remember, phi is a smooth function. It's a test function. Well, I guess I shouldn't say remember. I should point that out to you that phi is a smooth test function, so I can take its partial derivative of any order. This has to be equal to minus 1 to the alpha power, order alpha power, integral W against phi dx. Why did I choose this way of defining what I'm going to call this object called the weak derivative? It's because this is based on the structure of what we call integration by parts. So this is just an integration by parts formula. And think about it this way. If this function is classically differentiable, if this is classically differentiable function, now apply integration by parts in multi-D to that function, well, then the right-hand side I would get would involve no boundary integral because the boundary integral would be determined by the values of phi at the boundary, but the phi at the boundary is always going to be 0 because it's a C0 infinity function. And then the other function that you're going to get when you do the integration by parts is exactly going to be the partial derivative of v of order alpha. Exactly. Okay. I suppose an example will be helpful, and I'll show you an example momentarily. But this is just multidimensional integration by parts. And I'm cooking up this definition of the weak derivative, this guy right here, to fit into my usual slot as the classical derivative would fit. But I'm making this a weak definition by using what we call test functions. Now, if this weak derivative exists, it might not be the same as the classical derivative, but no problem. As long as it exists, it's going to be at worst an L1 loc function, which is a pretty weak function. It could be better than that, right? It could be, just because I'm saying L1 loc, it could be much smoother than that or much nicer than that. But I'm going to use the same notation that I would use normally for partial derivatives. Okay, I'm going to say partial alpha of v is equal to w, but I'm going to add this little w here, and that w stands for weak. It's the weak partial derivative. Now, before I get on to some examples and tell you what this thing is about, let me give you one property of these functions. A weak derivative, if it exists, is unique up to a set of measure 0. And how can I prove this? Well, I'm going to use the definition 4.1, and I'm going to use this little calculus of variations lemma that I already talked about, this lemma 4.1. How can I do this? So suppose that v is an L1 loc function that has potentially 2 alpha partial derivatives. So for example, the alpha weak partial derivative of v turns out to be u1, but it also, we can see in our supposition that it's also equal to u2. Is this possible? If this is possible, then u1 is going to appear in this location twice, but this is only going to appear once. So if I do this application of my formula, what happens is I'm going to find that I could possibly get 2 different functions appearing here for my candidate weak derivative. But this side is going to be exactly the same. So all I'm going to do is subtract the 2. If I subtract the 2, then you see that left-hand side just subtracts away to 0. And what I'm left with is the integral of w. Let's see, that should be, yeah, I think it probably makes more sense to call it w1 and w2. w1, w2, because I used w for weak derivative previously. All right, so integral w1 minus w2 against the same test function phi has to integrate to 0. But my little lemma said that anytime you have a L1 loc function, and L1 loc functions, if I add them together, I get another L1 loc function. It's pretty easy to show that. So this is an L1 loc function, and this is a test function in C0 infinity. Well, my little lemma 4.1 says that this has to be equal to 0 almost everywhere, but that just means that W1 equals W2 almost everywhere in omega. Okay? Last thing before we take a little break here is, if v is a classically differentiable function of order up to and including m, order m, then for each alpha, that's, wrote that wrong. A multi-index is there. That set of indices. If v is a CM function, then for each multi-index with where the multi-index order is less than or equal to m, the classical partial derivative is exactly equal to the weak partial derivative. That's because if I do standard integration by parts, then I get the same formula. Let me show you an example of this. So if I look at So I'm going to imagine that I'm in, let's make this a real example. So let's let d be equal to 2. So we're just in two-dimensional setting, right? So omega is open and bounded, right? Okay, so now let's look at, we can let m be kind of anything we want, but I want to focus on an example here where we're dealing with a very simple derivative. So the partial of phi with respect to x1, say. Now, in my two-dimensional space, d is equal to 2. In my two-dimensional space, I have two different first-order partial derivatives. Okay? Now, what happens whenever I take the partial derivative with respect to phi? You might remember the partial derivative formula that you have in this case. Let me see if I can remember it in this case. Um, should be integral, and if I get this wrong, I'll just issue a correction later. So you get a boundary integral, and I think that should be n1. So that's the component of the part of the outward pointing normal, but only in the one direction. Okay. Actually, let's do it like this. That's if I do it, yeah. So I can make it general. All right. So J could be either 1 or 2. It doesn't matter. All right. So then we have NJ. V phi. We have to integrate over the boundary. And usually the boundary increment that I use is ds. Now, when I do integration by parts, I also have another volume integral, or I guess in this case, an area integral. But now I'm going to throw the derivative over onto v, if possible. And the derivative leaves phi. And finally, I'm integrating over the increment. So in this case, what is dx? Dx is just equal to dx dy. Or I guess I should use dx1 dx2. Right? And then let's use the same thing over here. Same increment dx1 dx2. So that's, if you've never seen it before, this is the integration by parts formula for two dimensions where I'm just doing one derivative, or swapping one derivative over. Notice when I swap one derivative, I immediately gain this minus symbol. What happens to this boundary integral? Well, this guy is going to go away, right? Why does it go away? Why does it become 0? It becomes 0 because phi is a C0 infinity function, and as such, it always has to vanish on the boundary, okay? In fact, it has to vanish on the boundary even if it's not just the function's value itself, but it's it's a derivative. And so no matter what order I use, it's going to be equal to 0. So that's great. I can keep going, therefore. So I can swap or move more derivatives over, right? So that's why this formula has the structure that it does. If I keep doing repeated integration by parts, throwing more derivatives from phi over to v, ultimately I'm going to get the mth or the alpha partial derivative of v, if the thing is classically differentiable in the first place. If it's not, then I'm going to get something more general, and that's called the weak derivative. Okay, so I want to now give you kind of an example. This is a proposition, and it's definitely a useful proposition for us and what we want to talk about. The proof for this is a fairly simple little example, a fairly little simple little exercise that I want to go through. Suppose that v is a C0 function globally. Okay, so classically we can't guarantee that it has more than that it has even a standard first derivative. Okay, from AB into R. Right. So let's let P be a partition of AB. What does a partition of AB mean? It means that it's a set of points that are increasing, and the first point for a standard partition is equal to the left endpoint, and the last point of the partition is equal to the right endpoint. And all the points of the partition are otherwise ordered in this way. X0 is less than X1 is less than X2, up to Xn, right? So that's the partition. And we're going to suppose that for all k, so every interval in the partition, in other words, k equals 1 to n, v is a C1 function on that subinterval. Okay, so for every subinterval of the partition, every interval of the partition, that is, v is going to be a classically C1 function. So I could find a derivative. Now, it turns out v is not necessarily a classically differentiable function. I can give you an example of that, and maybe I will momentarily. Actually, there's one in the homework, which is a fairly good one. Now, however, v is weakly differentiable, and I can show that the first order weak derivative is precisely equal to this thing I'm going to call w star, where w star is just the classical derivative anytime that I'm inside an interval of the partition. Now, at the points of the partition, the specific points of the partition where v may have a jump discontinuity, where its derivative may have a jump discontinuity, I can define its derivative to be anything I want there. Doesn't matter. So I'm just going to say, let's let the derivative be equal to 1, just for giggles, I guess. So I want to show, using the definition, that this is actually the weak derivative. Now, weak derivatives aren't unique, but they're unique up to a set of measures 0. So I can change their definition on a set of measures 0, and it's not going to matter. And the reason that's the case is because weak derivatives are based on integral definitions, and if I change the value of a function on a set of measures 0, you know that that's probably not going to change the value of the derivative. How can I prove that? Well, I'm going to start with the left-hand side of my definition for the weak derivative. That would involve v and phi prime, just one derivative, one classical derivative of phi. And no problem taking derivatives of phi because phi is a C0 infinity function. Now, I'm going to break this. I'm going to start with this, but I'm going to break that integral immediately up into two integrals. The integral over 0 to 1/2 and the integral from 1/2 to 1. Why? That's because I'm doing a simplified proof here where the total interval is equal to 0, 1. So I'm just going to do a very simple partition where the partition is just going to be 0, 1/2, and 1. Okay, so the picture here is I've got a function and it looks like this. It's defined on 0 to 1. Okay, here it's doing something nice, and then it changes course and does something else. So what else could it do? Let's make it a linear. Okay, and maybe I'll line that up a little bit. Perfect. Okay, so it looks like it has a jump in its derivative. However, it is a C0 function, right? It's continuous at this point and a half. My partition is going to be 0, 1/2, and 1. And so I'm going to integrate over this first subinterval and then integrate over the second subinterval. And nice things may happen in that case. Okay, so this integral breaks up into this plus that one. I'm going to use integration by parts on this one and this one separately. Why can I do that? Well, because this is a classically differentiable function on these subintervals. Okay, so no problem doing that. I'm going to use integration by parts on this guy and that guy separately. If I do that, then my usual classical integration by parts formula says that I'm going to get boundary terms plus a new, what I'm going to call volume integral. But the derivative bounces from phi over to v, and I gain a minus sign, right? Now, one of these terms is going to be equal to 0. Because phi is a C0 infinity function, it has to vanish at the endpoint 0. So one of these 2 points is going to vanish, namely the one at 0. But let's not get there yet. Let's do integration by parts on this integral. Same thing. I get a boundary term minus this volume integral where the derivative is bounced from here over to here. Now, these 2 things might mean different things on these different subintervals, right? So here, the derivative is just going to be a negative everywhere, and since it's linear, it's just going to be some negative value like -1. And here it's something else, like it's some complicated function. But the derivative means 2 different things on these 2 different subintervals. I hope you agree with that. Now, the boundary integral, or the boundary term, remember this, when I evaluate at 0, that's got to vanish. And when I evaluate this boundary term at 1, that guy vanishes because phi is definitely going to be 0 at the endpoint 1. What I get by canceling those 2 terms, which, from the boundary values for phi, what I get are these 2 terms. Let me hold off on crossing those out a little bit. Okay, so pretend they haven't been crossed out yet. All right, so I get these 2 boundary terms remaining, and then these 2 volume terms. What about these 2 volume terms? Well, phi is certainly a continuous function because it's a C0 infinity function. What about v? We said v is a C0 function, so actually its value at 1/2 is going to be the same on both sides of the 1/2. Okay, so I'm going to approach 1/2 from this side and approach 1/2 from this side. Those 2 values of v are exactly the same, right? So this is my graph. I want to use black in this case. So this is v, okay, and this is x. So x along that axis. Well, this value and this value have to be the same, but now they're appearing with opposite signs because of my boundary terms. Now we know that those 2 things sum to 0, okay? So the combination of those 2 are 0. They sum to 0. Now what's left are these 2 boundary terms, and I can combine them together. Once I do that, then the combined definition of these 2 functions is precisely what I called previously W star. It was just equal to the derivatives in the separate subintervals, and I could redefine the derivative to be whatever the heck I want it to be at x equals 1/2. Check it out, okay? So I can recombine those functions into this grand function I call W star up above. Now, this is in the simplified setting because I changed my calculation from a generic interval to, to this interval with this very simple partition. But you can see how to expand this into a more complicated proof, or for the more general case. Okay, so I hope that getting a more general proof would be no problem for you. All right, so with a couple minutes left, I just want to state a couple of more properties of weak derivatives. The first property of weak derivative is that if I have 2 functions, both of which have weak derivatives, let's say u and v, and I add the two together or make a linear combination of those two functions, then that linear combination is also going to be weakly differentiable. And its weak derivative is nothing more or less than what you would expect. It's just the linear combination of the derivatives. So this says that the derivative operator is still a linear operator. What else? So the product rule still holds as well. If I know that u and v, the weak partial derivative of v of order alpha are LP-loc functions, and v, let's see, did I write that the correct way? I think I have to I think it has to be that way. So let me think about that. Yeah, okay. So if u and its partial derivative are LP functions and v and its partial derivative of order alpha is an LQ-loc function with alpha of order 1, so I'm only interested in the first order derivative in this case, then the product of those two functions, v and u, are weakly differentiable of order 1, and I have a formula for it. The formula is that the derivative of the product is the product of the derivative of the first times the second plus the product of the first times the derivative of the second. Okay, so those are two standard properties that one would expect if you would have classically differentiable function, and they hold in the weakly differentiable case as well. So I'm going to pause there. I'm going to stop there, and we'll end the lecture there today. Let me show you where we're going when we resume. We're going to talk about Sobolev spaces next. So I've talked about LP spaces and I've talked about the weak derivative. So if I combine those two things, the Frankenstein monster that emerges from LP spaces and weak derivatives are these things called Sobolev spaces. So that's where we'll pick up next time.